Now let us study the difference between the velocity formulation, which velocity formulations are applicable in this particular pictorial example. In example A, it is expected that only the flow near the impeller would be rotating, since the size of the impeller is very small compared to the entire CFD domain. So much of the flow away from the impeller would have a low velocity magnitude in the absolute frame. Therefore, solving using the absolute frame is recommended in this particular case. So in this particular case, we can use the absolute reference frame, and in the second case, we are going to see why we are going to use the relative reference frame. In case B, most of the flow is expected to be rotating with a velocity close to that of the impeller, hence the relative velocity formulation is appropriate in this particular case, because the size of the impeller is much large compared to the overall domain. So it is almost comparable to the overall domain, CFD domain size. So in this situation, we can go with the relative velocity formulation. But overall, in a situation between case A and B, either of the formulation may be used. This is just a recommendation which formulation is applicable to case A and case B. But we can use either of the formulation in both the cases, and it will give almost the similar type of results. Now, after selecting the velocity formulation, we have to set up the cell zone inputs. First, select the frame motion option button and click on the reference frame tab, which is this particular tab. We have to click here and this particular tab opens up. Here we have to provide all the types of inputs which are needed for setting up the moving reference frame problem. Now we will see one by one what all inputs are required. First input is the rotating axis origin, which is specified here. This is the rotating reference frame coordinate system origin. We have to specify the X, Y and Z coordinates. Next, we have to provide the rotating axis direction. After that, we need to input the rotational velocity, and if there is also translation motion, we have to provide the translation velocity components in all the three directions. We can directly give the zone motion using UDF as well. All inputs can be hooked to the UDF or profile files. UDF also permits prescription of transient variation for all frame motion inputs. Here, note that the rotational velocity is counterclockwise about the axis of rotation. Axis direction should be unit vector, but it will be normalized if not. Now there is also a UDF for transient inputs for moving reference frame. A UDF macro is available for this. This will allow you to write UDFs to control unsteady rotational and translation frame velocities. The physical time occurs in the argument list, and function returns the unsteady variable. Zone motion function option enables the use of single macro to set all frame motion inputs. This is more convenient than writing separate functions. We have seen setup and inputs for cell zone conditions for moving reference frame. Next settings are the boundary conditions. Let us list different boundary conditions that can be used here. Let us take one boundary condition at a time and see what are the different moving reference frame inputs required in their setup. We can use inlet boundary conditions like velocity inlet, pressure inlet, mass flow inlet, and outlet. We have the pressure outlet, non-reflecting boundary conditions, and the mass flow outlet. So a pictorial example here is seen. The blades are walls, the hub is wall, the shroud is a fixed wall, there is inlet as well as there is outlet in this particular axial pump problem. There are also wall boundary conditions, interfaces, periodic boundary conditions, conformal boundary conditions, and non-conformal boundary conditions. One by one we will study each of them and how to set up each of them. The first is the velocity inlet. The velocity inlet boundary condition is used for incompressible or mildly compressible flows. When inlet velocity is known, we can specify the absolute or relative velocity using the reference frame option. So here we select the reference frame option, and here we give the velocity components. We can specify vector components or magnitude and direction in Cartesian or cylindrical coordinates. For 2D axisymmetric problems with swirl and 3D problems, we can specify tangential velocity also. All these inputs come in this particular momentum tab of the velocity boundary condition. Now, flow direction is also important. We have to specify the flow direction as well. Now, when we specify the velocity inlet boundary condition, flow direction is another important criteria that we have to input. Flow direction is defined as the velocity vector normalized by its magnitude. Input allows Cartesian or cylindrical polar coordinate forms, and we have to note that the flow direction differs in absolute and relative frames. We have to use velocity triangle rule in order to calculate the flow directions. So we have to input the flow direction here. Next is pressure inlets. Pressure inlet boundary condition can be used for both compressible and incompressible flows. Definition of total pressure and total temperature will depend on the reference frame and compressibility. So in case of pressure values, that is total pressure, the consideration is in case of incompressible, it is considered as absolute velocity. When we are using incompressible relative formulation, this is the definition of the total pressure. When you are using compressible and absolute formulation, this is the definition of the total pressure and temperature. And in case of compressible relative velocity formulation, this is the definition of total pressure and total temperature. Note that the definition changes if you change the flow type and the velocity formulations, and the velocities change. In this case it is absolute velocity, in this case it is relative velocity. Again, in case of compressible absolute formulation, we have the velocities defined, Mach number defined using absolute velocities, and here it is relative velocity. So that is the change in the definition of total quantities like pressure, total pressure and total temperature. At pressure inlet, we have to specify the total pressure. So we have to specify the gauge total pressure value here in the pressure inlet boundary condition. Next, we have to also specify reference frame, whether it is absolute or relative, which is specified here. We also need to input the flow direction vector if we use the pressure inlet boundary condition, which is specified over here. Frame of flow direction depends on the reference frame input. If using absolute reference frame, we then input absolute. If using relative reference frame, we have to input relative. Other scalar boundary condition also required, like temperature, turbulence boundary condition, species, which are specified in the separate tabs here.